bagong project.
Ano na naman yan?
Ha? Ito, bago nating project.
Ano yan?
Ha? Yan ay tinatawag na light screamer using 555 timer. Meron doon 555 timer, may LDR, light dependent resistor, may capacitor, resistor, at may speaker. At meron tayong oscilloscope.
Para saan naman yan? Ano yan? Iba yan
Yan ay ginagamit para makita natin yung signal output. O para siyang X-ray ng kuryente, ng voltahe. Kaya may oscilloscope. Siya ay parang X-ray ng kuryente o X-ray ng dugo, kung paano dumalo yung dugo. Dito naman, siya ay voltage over a period of time. O para yung daloy ng dugo over a period of time. Parang ganon.
Ay, ano naman ang gagawin mo dyan?
Aba, susubukan natin yung tinatawag na light screamer. Lagyan natin ng supply. Ito, supply. Adjustable. $5 volts. May signal na Di ba? Gawin nating 9 volts. $9 volts. Medyo mataas na yung frequency ng speaker. Yun signal niya. May mga spikes. Di ba? Pag tinakpan natin yung LDR, yun nababago yung tunog. Tanggalin muna natin yung speaker. Yan ang pinaka-basic niya. Siya ay oscillator. Yun lakihan natin. Medyo madumi yung signal kasi nga may mga jumper wires. Kaya ganyan yan. Yung una niyang signal. So dito, lapitan natin. Diba? Pwede rin lakihan natin scale. Liitan, lakihan. So mapapansin mo rito, siya ay may positive voltage, negative voltage. Pero siya ay DC. Diba? Wala siyang offset. Kasi kung may offset yan, dapat nandun sa zero. Dahil doon sa capacitor yan. Okay, nahulog ang cellphone. Ayun meron siyang maximum voltage, 6.54. Yun. Minimum, negative 5. Negative 5 volts, Positive 6.7 volts. May positive and negative voltage. Diba? At yung gitna niya, wala siyang offset. Nahati siya sa positive at negative voltage. Voltage, peak to peak. Peak dito, tsaka peak ng negative, peak ng positive. 12 volts. Di ba? 12 volts Lumakas. Nag-amplify. Time division, 0.3 millisecond. Yan yung takbo nung oscillator. Parang ganyan yan, no? Yan, no? Tumatakbo. Diba? O, yung pinakamalaki na niya. Yan yung basic niya. Square wave. Na ngayon, since wala yung speaker, maganda yung signal. Pag nilagyan mo ng speaker yan, madi-distort. Okay, nahulog na naman. Lagyan natin ng speaker. Nadi-distort yung signal, oh. May spike, pero positive at negative pa rin siya. Ayun, oh. 13 volts. Pag walang speaker, siya ay may pagka-square wave, di ba? Pag tinakpan natin yung LDR, teka. Yun, LDR. Takpan natin. Yun, Pag tinakpan natin yan, nababago yung nag-e-expand. Expand, compress yung signal. Di ba? O, lagyan natin ng sounds. Tingnan mo, ha. Di ba? Okay? Expand, compress. Expand, compress. Ibig sabihin yan, nababago yung frequency. Walang speaker, yung kanyang pinaka-signal, expand, compress, expand, compress. Lumalaki, lumiliit yung kanyang on-off time. Nag-sweeping siya, ang tawag yan, sweeping. Sweep, lumalaki yung signal, lumiliit. Pag mababa yung signal, lumalaki yung waveform. Bababa yung frequency. Pag mataas, mas maliliit yung signal niya. Di ba?
Ang galing naman yan!
This is now our schematic diagram of a light screamer using 555 timer. When you say schematic diagram, that is the simplified version of circuit diagram. You're just simplifying the connection of the circuit in order to explain it clearly. So this is a simplified diagram or schematic diagram of the light screamer. So in our circuit, we're using 9 volt supply. And then pin 8, power supply of the IC. Pin 4, reset to be connected to 9 volts in order not to reset the circuit to continue its operation. Okay? Pin number 1, ground. Pin number 2, trigger. Pin number 6, threshold. They are interconnected. Pin number 7, no connection, which is a discharge pin. Pin number 5 is the control voltage. No connection. Pin number 3, output. Okay? And into the 2 and 6, connected is the capacitor, 0.1 microfarad to the ground. Also connected is to the pin 2 and 6 is the resistor with LDR, light dependent resistor. And then connected to the output. This serves as a feedback of the circuit because we are getting a feedback from output then back to the input. And into the output connected is the electrolytic. This one is ceramic type. This one is electrolytic. That's why there's a polarity, positive, negative. 10 microfarad, 25 volts. And to the negative side of the capacitor is the speaker. Okay, small speaker to the ground. It has a polarity, positive to negative, negative to the ground. So that is the connection of our circuit. What is the initial state of the circuit? What is the initial state? The initial state is capacitor is charging. So when you're powering on the circuit, 9 volts, current flows into the pin number 8, then to the pin 2, then to the capacitor, then to the ground, charging the capacitor. Also current flows into the pin number 6, and then to the capacitor, then to the ground. And also current flows into the inside the circuit. Since this is a integrated circuit, flows into the output, and then to the capacitor, and then to the speaker, then to the ground. Also flows into the feedback to the LDR 1K, and then charging again the capacitor. So when it is charging, there is an output. And what is the output of the speaker? What happened to the speaker? It will vibrate because the capacitor is charging. As you can see in the oscilloscope, okay, it is a positive voltage pushing the, okay, what happened to the pushing the speaker? So it will push the speaker positive because it vibrates. The cone of the speaker is vibrating, so it will push the cone of the speaker outward. So positive voltage. Okay, it creates a positive voltage as we can see in the oscilloscope, vibrating the speaker outward, positive voltage. And then what about the time the capacitor now is discharging? Where will it discharge? It will now discharge to the, since this is now the supply, it will now discharge before it is charging. Right? Now it is discharging through pin number 2, pin number 6, and then to the ground. What happened to the speaker? There's no current that will flow into the output. There's no current. It flows directly to the ground. So what happened to the speaker when the capacitor is discharging? The vibration of the cone will go back to its initial position. So it will vibrate again, creating a negative voltage, positive voltage. So this type of a circuit is an oscillator, right? It creates a positive and negative voltage. So the speaker is vibrating, pushing and pulling back the cone of the speaker As you can see, as we have seen in the oscilloscope, positive voltage, negative voltage. Positive voltage pushing the cone outward, pushing, and then discharging. It will now go back to its original position, creating a negative voltage. Positive voltage outward, then going back, negative voltage. So that's why this speaker is vibrating. It creates a frequency. Why is it that the circuit is oscillating? The circuit is oscillating because also with the help of this light dependent resistor. If we cover the LDR as we have tested it in our demo, it will create a dark resistance. It will increase the resistance of the light dependent resistor. It will increase the resistance. Okay? If this increase in resistance will make the vibration or the sounds, it will result into a lower frequency. So if there's no light, you are covering the LDR, it will create a high resistance. So there is the capacitor is charging slowly. But if you release your finger to the LDR, it will create a high frequency because there is now a less resistance to the LDR. That's the role of LDR into the circuit. It increases and decreases resistance. That contributes to the charging and discharging of capacitor. So there's a large resistance to this line. It's so hard to charge, so it charges slowly. If there's less resistance, it will charge much faster, right? With the less resistance. So that's the role of the LDR, increasing the resistance and decreasing the resistance. So if there's a light falling into this LDR. If the LDR catches a light or it decreases the resistance of the LDR. If there's no light, it will increase the resistance. That's why this one is responsible for oscillating the circuit, making it faster, make it slower, and the vibration of the speaker also make it faster, slower, and the sound is having this low frequency and high frequency signal. Okay? As I've said, this capacitor is responsible for what? For creating a negative and positive voltage. As in the figure or as in the oscilloscope, if we don't have a capacitor, the signal will look like this. This is now the zero. This is the zero. The positive voltage is located now here and negative voltage is located here. It is located into the first quadrant. Remember mathematics, first quadrant? But here, it is located into the first quadrant and the fourth quadrant. As you remember the mathematics, first quadrant, second quadrant, third quadrant, fourth quadrant. So this capacitor is responsible for making the signal to offset or not to offset If there's no capacitor, there is no offset. Still, this is a DC signal. It means it is flowing in one direction. Even there is a positive voltage and negative voltage. But here, there is an offset. What I mean by offset? It should be like this. It creates an offset. Offsetting the signal. Remember that the original signal is this. Now, it becomes like this. There is an offset. There is now what we call a virtual ground. This zero now is located here. And the positive voltage is here and negative voltage is here in the first quadrant. So, capacitor is responsible for that. But the sounds is the same. Well, it filters out the frequency also because it serves as a filter. Remember a filter? A filter should be a capacitor in series with a coil. And the speaker has a coil. So it serves as a filter. Or there is a resistance to the circuit, to the speaker. Okay? What is now the frequency when we cover the LDR? What is the frequency? When we cover the LDR, the frequency is around 579 Hertz. And what is the frequency when we don't cover the LDR? What is the frequency? It is 2.3 kilohertz. That is the frequency generated by this circuit. Okay? Why is it there is an oscillation into the circuit? We can see that in the internal circuitry of the 555. Let us see. Okay. Oh. That is the internal circuit of the 555. Why is it oscillating? Let us examine the circuit. Inside the 555, we have the 3 5K resistor. Connected is the op amps and then the flip-flop and then the inverter inside the IC. Why is it oscillating? Okay? It is oscillating because as we have talked before, or we are assuming that the circuit is, the capacitor is charging, the initial state, charging through where? From powering the circuit, the current flows into the pin number 8 and into the inverting. So, this is now producing 2/3 of the BCC. What is the 2/3 of 9 volts? Okay? 2/3, 6 volts. 6. And upon powering the circuit, the current flows into the pin number 8 and then to the non-inverting. If we measure the voltage here, it's receiving a 1/3 from non-inverting to the ground. This one is 6 volts because of the two divider or the two resistor. This one is receiving a 3 volts. That is just a 1/3 of the voltage. Huh? This one is 9 volts, 6 volts, 3 volts. And what happened to the other pin of the op amps? Since this is the inverting, the positive pin or non-inverting input of the op amps inside the 555 is connected to the threshold, pin number 6 threshold, which is connected to pin number 2 and to the capacitor because it is charging. So, it receives a 0 volts. Why 0 volts? Because capacitor is grounded. Okay? Now, why is it there is 1 and 0? Now, how about the other op amps? Then the negative or the inverting input of the inverting input of the op amp is also connected to pin number 6 and to the capacitor. Since the capacitor is charging, it receives a 0 volts. Okay? And into the rules of op amp. If the inverting is greater than the non-inverting, 6 volts is greater than 0 volts. 0 volts because capacitor is charging and grounded. 6 volts because it is connected with the two resistor to the ground that comprising 6 volts, which is equal to 6 volts. Right? Then the inverting is greater than the non-inverting. The output now is 0. That is the rules. The rules of amps. Now here, it is exactly the opposite of the other op amp. This non-inverting input of an op amp is connected to the 1/3 of the 9 volts. Why? Because there is a resistor connected to the ground. If you measure the voltage there, it is just a 1/3 of the 9 volts. But if you measure a voltage here to the ground, it is 6 volts. But here it is 3 volts because 1/3 of 9 volts is 3 volts. And the inverting input, since this is grounded by a capacitor, it will now become 0 volts. So, the non-inverting is greater than the inverting input. It means we are outputting a logic 1. What do I mean by logic 1? It is on. That is according to the digital electronics. And 0, it is off or low level. Okay? And we're now passing through this RS flip-flop. What is this RS flip-flop? This is a kind of a circuit, a switching circuit in digital electronics that is composed of reset and set input. Reset is 0, set is 1. Reset is directly connected to the Q complement. So if this is 0, reset directly to the output Q complement, it is also 0, directly connected. But here, it is the complement set. We need to complement the circuit because the original output of set is Q. But we are using a Q complement. This RF flip-flop has 2 outputs, but we are using only one output, Q complement. If this is 1, it will be complemented or inverted. It becomes 0. But here, reset, directly connected. Q complement or Q bar or Q nut. whatever you call that. There's so many terms used in this because RS flip-flop has two input, reset and set, and two output. Reset is directly connected to Q naught. Set is to the Q. But in our circuit, we're using only one output, Q naught. So if the reset is 0, it becomes 0. Okay? And we're not using the Q. So if the set is 0, it will complemented or inverted, it becomes 1. But if this is 1, it becomes 0. Uy! Wow! Okay, the whiteboard is flying. Let us see why is it flying. That is the operation of the RS flip-flop. So we're using the Q complement. Okay. And then we have this inverter. This is another form of switching circuit. Inverter. It inverts the 0 into 1. So it means that there is an output. There is an output into the circuit that will feed into the speaker and to the LDR. And then, what happened if the capacitor now is discharging? It's the opposite. Okay? Now the current will flow into the 2 and then to the 6. It is now the opposite of what we have. It will now become 1 and 0. Why is it that it becomes 1 and 0? The opposite of the charging. Because if this is 9 volts, charging at 9 volts, so it will become 9 volts. 9 volts is greater than 6 volts. It becomes 1. Right? Becomes 9 volts. 9 volts here is greater than 3 volts. Becomes, as I've said, inverting is greater than non-inverting. It will output 0. Oh, that's why there is 1 0. So it will make 1 here. Why? We are complementing it, or it is directly proportional to the reset. 1 here, and then it inverted. Going to invert the signal, 0. So there's no output, 0, low level. That is according to the digital electronics. Oh, that is now the analogy. Why is it, that is now the reason why is it oscillating. And it depends on the, where is the cup? And it depends on the light that falls, or light that falls into the LDR. If there is a bright light, will decrease the resistance. It will make to charge and discharge the capacitor very fast. If there is no light, it will discharge slowly. Charge and discharge slowly. There's a light, it will charge faster. If there's no light, it will charge and discharge slowly. That is the sensor. So that is the operation of the light screamer. Because of this sensor and the oscillator of the circuit.